So I'm not going to go over much of the syllabus, just kind of the big things that I'll get upset if someone emails me about because it's like, bro, it's right here. Um, so let's see. Office hours are every day, 1 to 3 p.m. Um, I guess today or any other day that's a snow day, you can just email me during that time and I'm happy to answer. I'm happy to answer email at any time. I'm pretty, I guess, chronically online because I'm always checking my phone for emails. And so if you have questions at any time of the day, please do email. Even if it's night or the weekend, I'll just answer when I guess, get to it. Textbook, I've sent out some information about that already. So it's Halliday and Resnick. And you'll need the Wiley Plus access. You don't need a physical textbook, but there is an e-text bundled with that access. So that's included either through Smart Start or you can get it through the bookstore directly. But I probably would recommend, if you're not going to do Smart Start, to go directly through Wiley to get it because it's cheaper that way. The bookstore has their surcharge on everything, and so it's more expensive. I'm supposed to shill for them a little bit, but it's just cheaper to go through Wiley if you don't prefer the Smart Start option. Let's see. The point distribution, really not a lot to say there other than the tests are not weighted too heavily. Homework is the big thing that'll get you. If you're not doing homework, it's going to drop your grades significantly. And with the way I have grades set up in Canvas, just be warned that any kind of loss of points early in the semester looks like a bad hit against your grade because it's just not a lot being averaged over. When we've only got like 5 assignments or 2 assignments to average over, and one of them has a couple less points than the other, the average drops significantly. So especially in the first month, don't worry too much about what the grade's saying. And that, before this assignment, I had an 80 and now I have a 75. What happened? It's just there's not enough assignments to get a good representative average. Let's see. Lectures and quizzes. So quizzes we'll have every week. I don't do pop quizzes, but sometimes if it slips my mind, kind of the rule of thumb is that if we finished a chapter in the previous class, we are likely to have a quiz the next class. So if you're not sure, I mean, you can email me, you can ask a friend, but if you're not sure, if we just finished a chapter, it's very likely we'll have a quiz on that chapter in the next class. They're not a big deal. They're 5-minute quizzes at the beginning of class, and they're always conceptual questions. I don't do calculation questions on the quizzes. I think that's the main things I want to get at in the syllabus, but please do skim through the rest. Make sure you just kind of know the ground rules getting going, but I don't want to dwell on it for too long. One thing that is very important is, so I'm going to show you here Gabby. This is my dog. She's kind of the unofficial mascot of all of my physics classes. So you'll see her popping up in extra credit questions on exams. I have stamps that, here's other pictures of her, but stamp you get on a quiz if you get a 5 out of 5. So you'll see her a lot. And so I just want you to know who this dog is before we get going. Let's see what else. If she was awake, I'd pick her up, but I don't think she's awake just yet. Okay, so Wiley, I know right now you'll still be getting access, although I believe it should be set up so that everyone can go to Wiley course resources right now. And it will let you'll have to sign in or create an account, but you'll be able to see everything. That is kind of based on the assumption that you're in Smart Start, although everyone has this access until the opt-out date for Smart Start, which I believe is the 26th. So up until the 26th, everyone should be able to access this. Past the 26th, if you're still in Smart Start, nothing should change. You should maintain access. But if you are not in Smart Start, if you've opted out at that point, then you will have to purchase access. And that should pop up when you try and go to this the next time. It'll say, hey, you need an access code to do this, and it should walk you through how to purchase one, and that'll be the cheaper option than going through the bookstore to do it if you've chosen to opt out of Smart Start. What else? So if I come back over here, I'm just going to show you kind of the basic structure you're going to see for each chapter. I do recommend reading this page guide. It goes through what each of these sections are in a little bit more detail and what is graded, because there can be some confusion on which of these things are graded, which are not. So that tells you exactly what is going to be graded. But you're going to see for each chapter, I'll post the guided notes as one of the first things. That was also in that first email I sent out. You'll see readings and videos. I wish it was not separated by section. I did not do that. I hate that it's like that, but it separates everything into sections. And so when a chapter has like 10 sections, there's just 10 of these. It's awful. But at the bottom is where you're going to see assignments. And I'll go ahead and leave student view for just a second so that you can see when we have a couple more assignments, what they'll look like. Okay, so adaptive practice is an extra credit thing that you can do. It will add, if you do 5 of them over the course of the entire semester and they stay open the entire semester, you get 5 points added to your overall grade in the class. So it is as good as it sounds. If by the end of the semester you have an 80 and you've done 5 of these, congratulations, you have an 85. They can take a little while. It depends on the chapter, how long it takes, but it's adaptive in the sense that if you get questions right, it takes less time because it asks less questions. If you get it wrong, it takes more time and you have to answer more questions. So you don't want to just guess and hope you're right on stuff. It's good to make sure on those because otherwise it can really draw out the time. But that is extra credit. Those are optional. And you only have to do 5 of the 10-ish we'll have. Practice is assignments that we'll do during a chapter. So they'll be assigned right when we start a chapter. I'll have the one up for chapter 1 later today. They will be due when we finish the chapter, or if that's a pretty short chapter, it'll be at least a week from when it's assigned. So that one should be due a week from today is, I think, when I'll set that one. Homework is slightly harder questions, and they're assigned at the end of the chapter. So on the day we finish a chapter, I'll assign a homework. I'm not going to do one for chapter 1 because it's just kind of review stuff, hopefully. So there will just be a practice for chapter 1. These others I don't actually assign through Canvas, so don't worry about interactive exercises or quizzes. We'll have in-class quizzes, again, like I mentioned earlier, as soon as we finish a chapter. All right, so I'm going to switch over to kind of how I take notes. This is not something that you have to take notes for. This is something that you can check out for the next 5-10 minutes if you want. But I like to start my Physics 1 classes by talking about research I did as a graduate student, so you can see what is going on in physics, engineering kind of right now, and get a sense of why we might be interested in physics to set the stage for what we're going to do. Because I'll be completely honest with you, Physics 1 is not the most interesting physics by far. It's probably the most boring physics you can take just by the nature of it. You can only talk about dropping a ball in so many different ways for so long before everyone mentally checks out. But the payoff is worth it in what you can study with those tools. So Physics 1 and kind of Physics 2 is like eating your vegetables. You got to get it over with to do the cool stuff. So my cool stuff was, as a graduate student, I studied things related to sonic booms. And so has anyone ever heard a sonic boom? Maybe you've heard it through a YouTube video or a movie or something like that. The only case where I'd expect that you'd hear it in real life, 2 cases. One, you were at some air show, or you were in some military related thing. Okay, so reserves or something where I guess there happened to be a base you were on where there was a flyover for some reason or another. That's my two guesses of if you've heard it, where you've heard it. The reason that you don't hear them in everyday life is because they're just super loud. So loud, in fact, that they're illegal to happen anywhere over land except for controlled airspaces like military bases, research facilities that NASA has, a few special cases like that. So I want to talk a little bit about what a sonic boom is, how they can become even worse than they already are, and kind of what's been done to mitigate them. Okay, so we're going to start over on the left. So right here, you're seeing a plane that is flying what we call subsonic. We characterize that by what's called a Mach number. That's just how fast the plane is going compared to the speed of sound. So a Mach number less than 1 means it's going slower than the speed of sound. And so these little circles are sound waves being generated by the plane. They're more complicated than that, but we're just going to pretend they're these spherical wave fronts spreading out from the plane. So larger ones are sound that was generated earlier in time because they've had longer to spread out away from the plane. Okay, so the ones near the plane were just generated, the ones far from it were generated a little while ago. And you can see because the speed of sound is faster than the speed of the plane, they can kind of move away from the plane before it catches up to the previously generated sound waves. But when we get to Mach 1, going at exactly the speed of sound, the plane is keeping up with all of those sound waves. So they kind of start to bunch up as more and more are generated. And so you get this kind of tangent line where there is a very high pressure. And that's what's sometimes called the sound barrier. You get a large, what's called wave drag at that speed, and you have to kind of have some extra oomph to overcome it, to get to faster than the speed of sound. So faster than the speed of sound, we don't get that just one tangent line. It's that the waves bunch up along this cone. In this case, the plane is actually overtaking the sound waves it generated earlier. It's getting ahead of them, and that's why we call it supersonic speed, faster than the speed of sound. And so the waves bunch up along what's called a Mach cone. You have to picture kind of a 3D picture here. And on that cone, that's what we call the sonic boom, what kind of leaves that cone and eventually reaches the ground. Okay, so that's your typical everyday sonic boom. Already very loud, similar to a somewhat nearby gunshot when you would hear it fly over. Here's how they become even worse. You have a plane flying. It's generating this Mach cone. Well, you may notice, just kind of based on this last picture up here, that the faster the plane flies, the more it gets ahead of the previously generated sound waves. And that's going to make this cone get narrower and narrower. Okay, so that's what we're seeing up here. This is a plane that's accelerating. It's getting faster and faster and faster. And so this cone gets narrower and narrower and narrower. The sound waves that leave that cone travel perpendicular to it. So we sometimes use what are called rays to talk about that motion, makes it a little bit easier to do the math. But what happens is when you have this particular case of an accelerating supersonic plane, those waves converge yet again on top of the fact they already converged on the Mach cone. They're going to come down some distance away from the plane and start to converge along this surface called a caustic. So if you've ever held a magnifying glass out in the sun, you may notice you can burn stuff with it if you were a particularly sociopathic child. So that is like a caustic. It's called a point focus, but the idea is the focusing of light in that case, in this case, sound. So that's where the word caustic comes from. It means burning because you could focus light to burn things. There are sound caustics where it's very focused sound waves. So on that caustic, things are even louder than the regular sonic boom. So, any guesses as to how much higher the pressure is on that caustic compared to the regular sonic boom? Okay, so the guess was about 2 times. And it can be about 2 times. It can actually be up to about 5 times the pressure. That doesn't actually mean 5 times louder than a regular sonic boom because the way the human hearing system works, especially for things as complicated as sonic booms, is kind of a nonlinear function of pressure. It's more complicated, but we can at least say as a kind of objective metric, pressure is 2 to 5 times higher on this caustic. So if sonic booms are illegal, how illegal do you think these super booms, that's what we call them, are? Pretty illegal. So people have been trying to model those super booms for a while. It's been at least since the 60s that there was research into this kind of sonic boom focusing is the term. This is kind of a depiction of where NASA set up a flight test. So the plane was flying up here. It generated this red caustic, and they set up a bunch of microphones along the ground. And so what you might notice that's a little bit interesting based on the blue rays, which kind of indicate where sound's going, is that on one side of the caustic, you apparently don't really hear anything. Then suddenly it gets very, very loud in this box because that's where the caustic touches the ground. Past that, you start to hear normal sonic booms because there's no longer focusing of sound. So this is a very weird thing. And in fact, this is more or less what was heard when they did these flight tests. Standing over here in what's called the shadow zone, they just heard what sounded like a distant rumbling, like thunder, miles and miles away. Right here, I kind of hope no one was standing right there because even with hearing protection, that might have been a problem. Out here, it was like your standard sonic boom sounds. So the red box is really the area of interest because that's saying what was someone on the ground where a caustic is touching the ground here. And so, like I said, lots of work has gone into modeling this. And there is an equation that's been developed to talk about the pressure in this region, both below the caustic, which would be in this shadow zone, above it, where sonic booms are normal, and right on it, where it's very, very loud. The equation is not pretty. This is it right here. So it's what's called a partial differential equation. And you can see there's a lot of terms. I could go through what every term means, but it's just accounting for different effects. Like this one's accounting for wind, so is this one in a different direction. This is accounting for things called thermoviscous absorption and atmospheric relaxation. This is nonlinearity, which is inherent in things really loud like sonic booms, so on and so forth. So, very complicated equation to describe this. But I'm going to show you next how this equation, which a human cannot solve, by the way, can only be solved numerically. You have to come up with tricks to approximate a solution because there is no sit down and solve this type of solution. But if you compare what this equation spits out to what was measured during this flight test, here's some of those graphs, okay? So the blue is the prediction from that nasty equation. The red is the flight tests. The Z bar thing you're seeing is just saying if you're above, on, or below the caustic. So Z bar greater than 0, a positive number, is going to mean you're above the caustic. And so you get what's kind of a typical signature for a sonic boom. It's called an in wave, and then you get this sort of focused signature in part of it. As you move towards the caustic, the two sort of overlap. And you get something about like that. And you might notice how the pressure compares. So the recorded one is close to 300 Pascal. This one's like 150. So you're getting about double there. And then below the caustic, so this is negative, you get this much lower signature, and it's much smoother too, much flatter. It sounds less intense even. And that's where we said is that shadow zone, where it gets like a distant thunder kind of sound. But I'd say the predictions are pretty good if you compare the red and the blue lines. Of course, you can always point out some areas where there is trouble, particularly in areas where there was not as much care put into the modeling, which would be especially this kind of shadow zone region right there. Part of that is due to atmospheric turbulence, which is not included in the model. So there are always more things you could account for, but it's pretty close. The reason all this research has been done is because they want to bring sonic booms back in a way that people are okay with. They were so loud, so annoying that so many people complained to the FAA in the 60s that in 1973 they were just banned, and still are now. But NASA especially has been pushing for a quieter supersonic airplane that generates quieter sonic booms. Now they're more focused on the regular sonic booms, these ones up here, compared to the focused ones. But what they've designed to try and overcome this difficulty is this thing, the X-59. So I don't know if anyone's been keeping up with the news on this. This thing's supposed to fly at Mach 1.5, about 900-ish miles per hour. And it's not a passenger plane. It's just X. In the X-59 means experimental. It's just to see if this idea works to make sonic booms quieter. Any guesses as to how loud this thing is supposed to be compared to a normal sonic boom?
About half as loud.
Okay. Supposedly, the design is supposed to produce a sonic boom that sounds not like a nearby gunshot, but like a car door shutting about, I think it was 20 feet away, is what they ended up going with. So it's so much quieter in theory, hasn't been tested yet, that they don't even call it a sonic boom anymore. They call it a sonic thump. So this, you could probably tell, is a rendering of this thing. Does anyone know when this thing is expected to take its first flight? Any guesses of what year?
No.
I'm
No
sorry,
idea. Like 28.
as a good answer. I think that's the most solid answer is I don't know. This year. So on Friday, actually, they unveiled the fully built plane, and it is set to take its first flight to see if this worked this year. I got to work with the team who was part of the design process, but also part of this next thing they're going to do, which is flying it over different communities to see how they respond to it. So they're going to go to a bunch of different cities, send out surveys, ask people what they thought, if they even heard it, like time of day, if they were more disturbed by it, that sort of thing, to see if it interferes with everyday life. And if it doesn't, then they could present this information to the FAA and say, hey, we have a path forward to something that could bring back supersonic flight, which for us, probably more like 10, 20 years down the line, means faster flights. And in fact, eventually we may have flights that are half as long, even anywhere over land. So this used to be a thing that was only good for over the water, and even that was kind of a novelty. That's what the Concorde was about, if you've heard of that. This thing can do, in principle, all of that over land if it can be kind of adapted into a passenger plane, a civilian transport. I'll show a video of it in a second, but does anyone notice kind of any interesting features about this plane compared to a regular one?
So the giant nose on it.
Yeah, very long canopy, very strange sort of shape. So that actually is exactly what makes the sonic boom quieter. Is when I talked about a sonic boom up here, I actually kind of lied about what it looks like. So Mach cones are actually generated everywhere along the length of the plane. and they have different angles depending on where on the plane you are, because the speed of sound at those different points varies because of just very complicated changes in pressure. So what this plane does is takes advantage of that to make sure that the sound that reaches the ground doesn't look like this, what I call an in wave, which is very jarring to people. It happens in the span of a few hundredths of a second, but is very jarring to hear. Sounds like a gunshot because, in fact, a bullet produces a sonic boom. Instead, it takes that thing, this very converged sort of wave, and spreads it out into something that looks more like that. And that is happening exclusively because of the shape of the plane. You may even notice, I think in the actual one, maybe it's not in the render, but there's a little spike on the front too, in the actual one, and that is further mitigating it. Any other kind of strange features?
Wings.
The wings, yeah, so keeps this kind of narrow body line, and that is further contributing to the shaping of the plane to make sure we get this quieter sonic boom, this kind of spread out one that's not as jarring to our senses. Look at the front of the plane, right about there. What's missing?
Is it dented?
You could say that it's a little bit dented with the shape of it, but what would the pilot want to have right there?
Oh, doesn't they want a window?
It doesn't have a window. So what's up with that? Apparently, as far as the design process went, to maintain the shape needed to keep this thing quiet, as far as the sonic boom that reaches the ground, they couldn't have a window right there. It would interfere too much with the shaping of the plane. And so it has no front window. Instead, they have this camera system inside the plane that simulates what they'd see out the front, which scares me so much to think about. But that's what they've come up with to kind of work around that problem. And so I'm sure it has plenty of redundancies to make sure they don't kill a pilot. But man, that is such a weird thing to me. Okay, so like I said, this is a render. I'm going to pull up a video real fast of their kind of flavor reel for this thing. So this just came out 5 days ago. So every semester I do this, but I like that finally I can actually show a real thing. So this is the first time I get to show some of this. Hopefully everyone's hearing that. It's just dramatic music though. So funny when nerds try to make stuff look cool. So it is supposed to fly this year, and hopefully it will produce that sonic thump we're all hoping for. There's been so much validation testing in what's called computational fluid dynamics to make sure this thing does that. It's almost a certainty that it will, but weather can affect it, and there's been studies into how much, and so there's still some uncertainty, but be on the lookout for that. If it does a flyover in a nearby city, I may go out just to see if I can hear it. But I mean, that is kind of a historical thing if you think about it. It's the first sonic boom you could hear over land in, let's see, what is that, 50 years? So why do I bother talking about all of this other than that it's interesting? For physics, what I take away from this, what's interesting to me about physics, is that if you study some phenomenon that happens in the natural world, or this gets into kind of the artificial man-made world long enough, you can get a really deep understanding of it. So much so that you get to the point where you can predict how it's going to play out, even without having experienced it yet. And so the value of physics is that predictive ability. It lets you get a deeper understanding of the world, but it also shows and lets you appreciate how ridiculously complicated nature is with whatever it's doing. Because I don't think it's solving this equation with a really powerful computer. I don't know what it's doing, but whatever it is apparently more complicated than this, because that equation doesn't account for all of those little extra pieces, all of those differences. As much as we try, nature is always a step ahead on exactly what it's doing. And the best we can do is get a approximation that gets a little bit better each time we take a pass at it. And that's what I want to stress at the outset is physics, everything we do is in some sense an approximation. The deeper you get into physics, the better that approximation gets. You hear about things like quantum field theory is the current like best approximation of anything, most successful theory in physics. But it's still an approximation. There's still little wiggles that we miss that nature still has. But we can still get close enough that we can develop new technologies to let us understand more about what's going on, better our lives. That's more on the engineering side of things, but hopefully physicists are giving a little kick that's needed sometimes to make some of that happen. So that's what I find interesting about physics. We'll see bits and pieces of that as we go. Like I said, physics 1 can be dry, but I want you to keep in the back of your mind that there is something at the end of it that isn't. And maybe that'll help you get through those days where we've been talking about dropping a ball for the 5th time, because there will be those days. All right. So with that, I want to get started on the actual notes. Anyone want to take a stab at what physics studies now that we've kind of seen one example?
The study of moving things.
So motion is a very important part of physics. So that's going to be actually one of my bullet points down here. So we do study motion extensively. And in fact, physics 1 is basically the study of motion, mechanics.
Like tangible things?
Okay. So I'd say yes. Can you be more specific about like what kind of things we would study?
The behavior of like certain things, like a material or something?
Okay, so like material properties, that is something that's of interest in physics. And that would go into this bin, I'd say, of atomic structure. I got that over here. So kind of gets into chemistry a little bit too, but how things come together and what that says about the properties of a material. Yeah. What else?
Would force count?
Yeah. So forces are a big part of it. And they are what cause and change the motion of something. So that's the other piece of mechanics that we're going to look at called dynamics.
Like energy or pressure?
Yeah, energy. Pressure, I agree on. I'm just going to say it sort of falls under the scope of forces because pressure is kind of a force density. It's a force per unit area.
Sound waves?
Yeah, sound. Yeah, I sure hope someone was going to say that one. It would validate my whole graduate career.
The gravitational like force between planets?
Yeah, somehow I've never put the bullet of gravity, which is just the dumbest thing with me, but yeah, I'd put gravity in there for sure. It is a force through one view of things. You hear about relativity where it is not viewed as a force, but yeah. Can anyone at this point, how about this? I'll give you the rest, and I want someone to try and see what these things have in common. Okay, so I'd say momentum is another big thing in physics. Electricity, magnetism, light, and heat. So motion, forces, energy, are mostly physics 1, as is momentum. Electricity, magnetism, and light are physics 2. Sound, heat, and atomic structure, I believe you get into in physics 3. I haven't actually taught that one yet, so I'm not sure exactly what y'all do, but usually that's the kind of the leftovers, the redheaded stepchildren of physics, unfortunately. So what sums all these things up?
This might be stupid, but they're all real.
Okay, I don't think that's stupid. I think that is actually a good thing to ground ourselves and what distinguishes physics from math, for instance. Math studies some things that are purely hypothetical, purely mental structures. And that's, I enjoy that side of things. That was one of my other degree was in math. So it's an interesting thing, but physics always has to come back to what's actually happening. If you have a physical model, no matter how pretty the math works out, if it doesn't reflect reality, it's not a good physics model. And so you have to throw it out. So that is a very important factor in physics. I think this is a thing where it's like there are a lot of right answers. There's just one word that goes in my little blank. So how about this? Someone try and define for me what energy is.
Is it the ability to do work?
It's a great definition and more or less the one we're going to go with. But what is work?
Doesn't work like force over a distance,
Okay, so what is force?
like mass times like acceleration.
Okay, what is mass?
Stuff.
This is what I'm getting at. Eventually you get frustrated with these questions, and everyone does, and there will be questions like this where you'll ask me and I'll say, I don't know. And there will be questions like this where nobody knows the answer. You get to such a basic level of the thing, not in the sense of simple, but like fundamental, that it becomes hard to define things anymore. It becomes hard to say what they even are. And that's physics kind of bread and butter, studying those things that you build off of for everything else. We talk about energy every day for so many different use cases because it factors into so many different things in the modern world. But it's hard to say what it even is when you kind of get down to it. So that's what physics is. Study of basic things, meaning things that are fundamental to how we understand the world. And kind of the unfortunate side of it is the more basic you go, like the more fundamental your understanding tries to be, the harder it becomes to make sense of any of it, and the more unintuitive and nonsensical it becomes. So we study mechanics, which is a first pass at understanding of motion, energy, and all those things. You could go further into quantum mechanics, which is a second pass where you're like, but I really want to know how everything's moving, how the electrons are behaving within these atoms, and how that adds up to produce these everyday things I see. You could go further than that and say, okay, but these electrons are actually moving around really, really fast. And so we have to account for something called relativity. And that leads you into something called quantum field theory. And that the math in that is absolutely intractable for most mortals, including me. So it just gets worse the deeper you go. But that's kind of the thing we have to put up with if we want to understand things better. So physics is the study of basic things. And so if you want to understand any science, they build off of physics. It's the thing at the bottom of all of that. That's not to say it's better. It's just the thing that technically sits underneath all the other things. You could argue math sits under it, and then logic sits under that, but I'm not going to go down that rabbit hole. Now we get to the boring stuff that we have to get to, which is just kind of recap stuff, a little bit of math, and then we'll get into studying motion. That's the first thing we look at. In order to conduct these experiments, like with the flight testing that was done for other planes in preparation for the X-59, we have to be able to have measurements that actually mean something, that say something about what we're measuring. And so we have to be careful about how we take measurements. They need to be accurate, meaning they need to reflect what we're measuring, obviously. They need to be reproducible, meaning someone else can check our work. And be confirmed by others. So the first step in that process of having accurate and reproducible measurements is having good units. You're all familiar with units. You know what they are. Give me some examples of units.
Meters.
Yeah, meters. What else?
Pounds.
Pounds. Yeah. So why do we use these things? Well, we didn't always. We used to use kind of even more arbitrary measurements of things. And that's where terms like feet came from and pounds. And most of the imperial system is based on very arbitrary measurements with like horse carriages and grains and just whatever was on hand, I guess. So we need to ask ourselves, what's a good unit? And so I could, for instance, use my height as the unit to measure distance. I could just lay down on the floor, scoot myself along until I've basically measured out whatever the distance is I'm trying to measure. Why is that a bad unit of measurement?
Because it can change.
It can change. Great. Depending on the time of day, your height changes. When you wake up in the morning, you're usually a little bit taller than when you go to bed because your spine compresses from the weight of your body. So it's not a very accurate measurement. It changes over time. And unless, I fly to France because they need me to measure the height of the Eiffel Tower by climbing up it or something, they have no way of getting my height as a measurement. Okay. Especially if it changes day to day. So it's not a good unit. You need something that's consistent and something that everyone can agree on the value of. So a unit is a way we measure a physical quantity. I'll abbreviate quantity QTY, defined in terms of some standard. And so we already said a couple units. So there was meters. That is the unit we tend to use for length. Seconds for time, and we'll get to the others in a minute. So standard, that might be the new part for you. It's that part of everyone needs to agree on what it is we mean by a meter or a second. We can't have any ambiguity in that because that could lead to error that has nothing to do with the experiment. It's purely to do with our measurement system. And so that's why we have these very specific standards of what a second, a kilogram, or a meter are. There are standards for these others too, but these are the main three we'll use in the class. And they are going to look very arbitrary because they absolutely are. So 1 second is defined as the time it takes for this many oscillations of light emitted when electrons move between two energy levels in a cesium-133 atom. So what the hell, right? Any ideas why we would use something like that as a standard?
Because it's something that's consistent.
Yeah, exactly. To the best of our knowledge, the frequency and so the time it takes for the oscillations of electromagnetic radiation emitted from an atom, it's such a consistent number based on the theory of quantum mechanics that we have almost no uncertainty about the fact that it is going to be this number of oscillations. We'll take a fixed time every single time. And so we just choose the amount of oscillations that is closest to what we previously thought of as a second, right? When someone first decided on, let's call the unit of time a second, they hadn't thought of this. They were talking about like some fraction of the length of a day or something. But this is just something that is incredibly reliable and is in fact what atomic clocks are based on. If you've heard of those, they're the most accurate way we have of measuring time, where they have an error of 1 part in a couple million over a century or something like that. So very consistent measurement is the important bit. And we like to have these units based on physical things, because then we have no say in how they happen, right? These oscillations of light just happen. Similar for kilograms, this one actually was just recently redefined this way in 2019. Before, it was even more arbitrary. It was the mass of a certain cylinder that's kept in, I think, France, maybe Sweden, I always forget. But it was made of platinum and iridium, so it was very inert, but it was just a hunk of metal. Now, a kilogram's been redefined as, this is one way of putting it, the change in mass of a certain number of CCM atoms after there's a transition between energy levels, because there's something called mass energy equivalence that says there is an equivalent amount of energy associated with any amount of mass. And when you have some change in the state of some system based on the energy of it, you have a change in its effective mass and vice versa. So also very arbitrary, but this is the thing that closest fits what we previously thought of as a kilogram. And a meter is the distance light travels in a certain fraction of a second, since we've already defined a second at this point. So you now never have to remember those standards again, because they're really not important in the grand scheme of things. No one's going to ask you to double check your measurement against these, but it's good to know what a second is, what a meter is, what a kilogram is at the core of it. The other thing we need to talk about is base quantities. Physicists like to build from the ground up, and so have as few pieces, as few assumptions as possible to get to a theory of something, and that includes how we measure things. So base quantities are physical quantities which can't be expressed in terms of each other. And we measure them. I'm going to use that abbreviation for width, measured with what we call base units. And that's what this table right down below is. So base quantities are also something that we're all familiar with. We've probably not heard it called that. They are things like time, mass, and length are our big three for physics 1. So the quantity, base quantities on the left, the base unit is on the right in the SI or metric system, which is what we use in physics. And if you continue in engineering classes, especially thermodynamics, you're going to hate how many different unit systems there are, because this is far from the only one. But this is the one we use in physics because it's based on powers of 10, and that's a very nice property that for some reason the imperial system does not have. Imperial meaning feet, pounds, things we're used to in everyday life. So what is the base unit for mass?
Kilogram.
Yeah, it was a good guess based on the standards part. It might seem odd that it's a kilogram instead of a gram. It's just because humans naturally have a better sense of what a kilogram is than a gram. If you hold something in your hand, you're probably more accurately estimating the number of kilograms it is than getting down into the grams. And so the SI system is kind of based on that idea of human scale measurements. But that's going to mean some things that get very small or very large are not well expressed in these units, and we'll get to that in a bit. So what is this part about can't be expressed in terms of each other?
Does that mean they're like unrelated to each other?
Yeah, I think that's a good way to put it. They're things that we cannot talk about without introducing a new concept for it. So if you just had time as your only way of measuring things, you would never be able to measure a mass of something, an amount of something. It's just not possible with a stopwatch. If you had a meter stick, same deal. You could argue there's a relationship between time and length as far as the speed of something, but then you'd call speed your base unit and then introduce one or the other in terms of it. So these are just the kind of set of things we can build off of. There are building blocks for other units. And there are ones for other things. Electric current is the ampere. So we'll see that in physics too. Oh, I need my abbreviations here. Kilograms. Ampere abbreviated capital A. Weird thing about units, if it's named after someone like ampere is, the spelled out word is lowercase, the unit is capitalized. Don't know why. Temperature measured in Kelvin in the SI system. Okay. Amount of something, the number of something is moles, which is more in chemistry. And luminous intensity. I have never ever in my life seen this one used in anything, but apparently it is the SI unit for luminous intensity, candelas. I'm used to seeing like lux or watts per square meter, or many other things other than candela. Anyway, so those are our base units that we measure things in. And then there are things we call derived units. They are units expressible in terms of two or more base units. So two or more, 2 plus base units. Can anyone think of an example of a derived unit?
Volume.
So volume, yeah, you could say is cubic meters, meters times meters times meters. So a length times a length times a length. That's a good one. I'm trying to think of one that's got a special name. Anyone know the unit of force?
A Newton.
Yes, perfect. So, and you could say a pound as well. That's a unit of force. We're used to using it just for weight, but it can measure any force. So a Newton, which is abbreviated capital N, it is defined as 1 kilogram meter per second squared, which sounds odd. We'll get to later that it's the amount of force required to give a 1 kilogram mass an acceleration of 1 meter per second. But that's where that kilogram meter per second squared thing comes from. So the Newton would be our derived unit. And these three would be our base units. So any unit you can think of can be built out of the units in this table. And that's the idea, is having the least number of things needed to describe any physical quantity. So, like I said, if you start to measure big or small enough things, then those units start to become a little bit unwieldy to use. And so we also use prefixes or powers of 10, or we use scientific notation. And I know you're all familiar with this, or hopefully so we'll go through it fast, but we need to just make sure we're on the same page on this. One thing that is worth mentioning early on before you do any assignments is this right here. Wiley doesn't use normal people scientific notation for assignments. It uses capital E, which is more like what you'd see on a calculator. So you may have a double E button on your calculator to do scientific notation. But just remember that when you're doing assignments, because I've had people go through a whole semester where they would write like 3,561,728 or something with even more digits rather than using scientific notation because they didn't know about this. So make sure that's something you remember on assignments. Okay, so like I said, certain things like say the radius of the Earth start to become a little bit difficult to measure in our standard units like meters. And so we use powers of 10 or scientific notation. So how would I express this in scientific notation?
I think it would be 6.378 times 10 to the 6th power.
Yep, sounds good to me. So 6.378 times 10 to the 6th. And we get that 6 because we have to move 1, 2, 3, 4, 5, 6 decimals to get to our first digit. So 6.378 times 10 to the 6th. We could also, so that's meters. We could write that several other ways. So if we look at our list of prefixes, we see that 10 to the 6th corresponds to mega. So although you never hear any sane human being write it this way, you can also write it as 6.378 megameters. You could also write it as, okay, I could split that 10 to the 6th into 2 sets of 10 to the 3. And then I just group this into 10 to the 3 is kilometers, kilo. And then I just multiply the first part out. It's 6,378. So I could also write this as 6,378 kilometers. And I think that's a lot more common of a way to talk about the radius of the Earth than megameters. We could go the other direction. The mass of an eyelash is a very small amount of kilograms, and so we need a lot of decimal places to talk about it. So how would we talk about this in scientific notation?
Is it 7 times 10 to the negative 7?
So let's see. If I want to get this decimal back, we do 1, 2, 3, 4, 5, 6, 7. One more. I have to do 8. So very close. It's 7 times 10 to the negative 8. Kilograms. I could write that in several other ways. I could write it as, okay, kilo is 10 to the 3. So 10 to the 3 grams. And so I could write it as 7 times 10 to the negative 8 times 10 to the 3 is 10 to the negative 5. So 7 times 10 to the negative 5 grams. I could also write that as 10 to the negative 5 is 10 to the 1 times 10 to the negative 6. All right, so I'm just saying I could split that into 2 parts. Still grams. And the reason I might do that is because 10 to the negative 6 is in my list of prefixes. It's called a micro. So I could write this as 7 times 10 to the 1 micrograms. If you have your calculator set in scientific notation, it'll always do this. But if you have it set to engineering notation, is what we usually see it called, it'll do this. It always tries to get to the nearest power of 3. It's just a way of expressing it in terms of one of the prefixes and getting to the nearest one. So just being able to jump between prefixes is a good skill. Okay, unit conversion, another boring but necessary piece. So we said there's multiple unit systems. Imperial is the one we're used to in everyday life. That's the US or US system. There's also SI is the one we like to use. In especially engineering and thermodynamics, you'll occasionally see BE, British engineering. That's where you see BTUs, foot pounds, slugs, all these stupid units. And CGS is centimeters, grams, seconds. So it's almost SI. It's just someone liked those units better for some reason. So that one's a little bit rarer. But anyway, we want to be able to convert back and forth. So let's start with a very easy question and then overanalyze the hell out of it. So how many seconds are in 2 hours?
7,200.
Yeah. So I'm gonna make some space, 7,200 seconds. So how did you get that? What did you do?
60 times 60 times 2.
60 what?
60 seconds times 60 minutes. But I don't know what right units that'd be.
Exactly. And see, that's the thing is we don't think about it that way. For some unit conversions, we're going to have to. And so that's the idea I want to get across is somehow we traversed from hours to seconds. That should work out algebraically just as well as 2 times 60 times 60 did. And by that, I mean 2 times 60 times 60, we're used to everyday algebra of regular numbers. There's also algebra for units. And we want to make sure that algebra also checks out. So there is a mathematical way we end up at seconds from hours, and that's by using what we call conversion factors. So I need a little bit more space there. So really what you did is you said there's 60 minutes in 1 hour. And then you said there's 60 seconds in 1 minute. Those were the conversions you naturally did in your head without ever worrying about what the units actually were because you know implicitly. But if I write it out like that, I notice that the units actually work out. Hours, if I treat it as an algebra thing that I can cancel and multiply like anything else, cancels hours. Minutes cancels minutes because they're in the numerator and denominator. What am I left with? Seconds, which is the unit of the right-hand side. And so if we set up conversions like this, the units always work out properly, and we make sure we've done every conversion needed to get from one unit to another. So we call these things conversion factors. We'll sometimes also see them written as 60 minutes equals 1 hour. And similar for seconds and minutes. And so the definition of a conversion factor is another very weird sounding definition that's just more complicated than it needs to be. It's a ratio of units equal to 1. What does that even mean? It just means 60 minutes and 1 hour represent the same thing. In effect, they are the same number. 60 does not equal 1, obviously, but 60 minutes equals 1 hour. So if you express or include the units, that is an equality between those two things. Or in other words, when you divide them, you divide both sides by 1 hour, you get 1. Okay, I'm saying if I divide both of these by 1 hour, that cancels, you're left with just 1 on the right-hand side. And that's what they mean when they say a ratio of units equals to 1. So for any unit conversion, here is your process. I think of it a lot like translation, with the idea that you start with one way of expressing something and you come up with another way of expressing the exact same thing. And the way you do it is through a translation. For units, it's a conversion factor. For everyday or for languages, it's whatever you use to translate. You may just know the language or you use a dictionary, whatever. Okay, so you figure out what it is you're trying to convert, what you want to convert to, figure out your path from one to the other. Sometimes you need not only a quote unquote Spanish to English dictionary, you also need, if you're trying to convert to Swedish, maybe you need an English to German dictionary because you couldn't find directly to Swedish, and then you get German to Sweden, right? You need multiple conversions to get from one thing to the other. You write them out like we did up above, so that any units you don't want cancel out along the way, so that you end up with only the units you do want. And then this is an important step that's often overlooked. You want to make sure your conversion actually makes physical sense, right? You can get all of this correct up here, but accidentally write that there's 1 minute and 60 hours, and you flip that, you get the reciprocal, and that messes up everything. So you want to make sure that you know for a fact that your conversions are real relationships between those units. And then you just multiply across. So I want you to take a minute, I only have a couple minutes, to convert 20 meters per second to miles per hour. That's a slightly harder one, but maybe gives you some sense of the value of this idea of conversion factors. And by the way, if you on assignments start to do this just through Google, I won't judge you. I hate the amount of conversions that the Wiley assignments include, but it is good to know at any point that you could do it on paper. So just make sure you're at that stage before you start Googling all the unit conversions. I'm still working it out, that's fine. I'm just gonna kind of start saying some things for anyone who's not sure how to start. So what would our input units be in this case? What are we starting with?
20 meters.
Not just meters, but meters per second, right? Okay, what's our output units? Right, miles per hour, thank you. So we're trying to get from meters per second, and I like to use the abbreviations when I'm doing the conversion, to miles per hour. I need some path from one to the other. So I need some conversion factors. What are some useful conversion factors here? I've already been given one.
You need to go from kilometers to meters.
Yeah. So you need a conversion between meters and kilometers. So what is that conversion?
Is it just 1,000 meters over 1 kilometer?
Yep. So you can write it as a ratio, you can write it as equals, and then put the ratio in down here. I'm fine with either. Either is the correct answer. Okay. I still need a way to get from seconds to hours. We could go this route like we did for this question, or you could actually realize that these two together make up a conversion factor. And that conversion factor is, if we just think of minutes canceling, because we're not including 2 hours, the thing out front in this conversion factor, it says there's 3,600 seconds per 1 hour. Okay, so that's also a conversion factor. And so that's going to be kind of the shortcut. And that's the idea, is the more conversions you do, the larger your bank of conversion factors you've built up. So I think now I have a way somehow to get from meters per second to miles per hour. I see things with all of those units in it. So how I do this is, without worrying about the numbers just yet, I just put things in so that these units will cancel. I know I've got a conversion between meters and kilometers. I put meters on the bottom so that they'll cancel with the meters up here. Okay, but I'm still not in my proper units I want to end up in, miles per hour. So I need my conversion from kilometers to miles. I want to get rid of kilometers, so those should cancel by being on top and bottom. And so I convert to miles. And last, I want to convert seconds to hours. Now here I got to be a little careful. Seconds are in the denominator over here. So to cancel them, I want seconds in the numerator in my conversion. And then I want to go to hours. That's my output unit. So, oops, cancel, seconds cancels. And if I look across, what I'm left with is miles per hour. That's the only units that didn't cancel. Okay, now that I've done that part, the rest is easy. I just put in the numbers from my conversion factors. I said there's 1 kilometer in 1,000 meters. I said there's 1 mile in 1.61 or 1.609 kilometers. And then there's 3,600 seconds in 1 hour. And so if I multiply all those things across, I will get my number in miles per hour. So 20 over 1,000 over 1.61 multiplied by 3,600, 44.7 miles per hour. And the last thing I'll say is, just like with the shortcut for hours and seconds, that one right there, I can multiply all my conversion factors to get a new conversion factor relating miles per hour and meters per second, so that I never have to do this again. I get 2.236 miles per hour per 1 meter per second. In other words, 1 meter per second equals 2.236 miles per hour. And now you never have to do this conversion again. You've got the shortcut. Okay, so that's kind of your roadmap to doing any conversion, no matter how complicated. And there will be ones where you got to go through like 5 different parts, but it's the same process. It's just more things to multiply by. Okay, last thing I want to say is I'm going to post some other examples on Canvas. They'll be under like an additional examples page. And so if you're ever not satisfied with the number of examples we do in class, I'm going to do my best to post a few more for each chapter that you can watch on Canvas. All right, well, if there are no other questions, I will see you all hopefully in person on Tuesday. Again, I really hate Zoom lectures. I know you do too, but it's all we could get away with today. So anyway, I'll see you all on Tuesday and hopefully get to meet you in person.
Sounds good.
All right, everyone have a good day. Stay warm.